microhydro system is one of the oldest and most reliable renewable energy options available to us. We are here to teach you about the feasibility study for microhydro systems. But first, let's acquaint ourselves with the key components of a microhydro system. In general, microhydro schemes are made up of 6 key components. The intake is where water is diverted into a dammed pool from a stream, river, or waterfall. The intake structure is normally constructed from a combination of steel, stone, and concrete, and contains a catch box with a screen to filter out floating debris and fish. From the intake, water is transported through the head race, which is a canal or pipeline made from concrete, steel, or polyethylene pipe, into the forebay. The forebay, or sedimentation tank, is typically a concrete structure that separates sediment from the water. From the forebay, water travels into the penstock, which is a pipeline that can be constructed with steel or polyethylene, with concrete, wood, and/or steel support structures. Water builds up pressure as it travels through the penstock into the turbine located at the powerhouse. The powerhouse is where a turbine converts the pressure and flow of water into mechanical energy. The turbine powers a generator, which then converts the mechanical energy into electrical energy. Electricity is then transported to consumers via a transmission and distribution line. When conducting a feasibility study, we are working to determine the estimated size of a system in kilowatts. Second, we're trying to understand the distance between the key components we just discussed, both in terms of vertical distance and horizontal distance. Third, the level of community readiness to undertake a microhydro project. And finally, the estimated cost of a system as influenced by the variables that I have just mentioned. To determine the system size and distance between key points during a feasibility study, we are looking at 3 key variables. First, we're looking at head, which is the vertical distance between 2 key points expressed in meters. Second, we're looking at flow, which is the volume of water passing through a given point over time, expressed in liters per second. Third, distance, which is the horizontal distance between certain key components of the microhydro system. The total power potential of a microhydro system can be expressed in the following formula. Before moving into how we go ahead and measure these key variables, let's highlight the things you'll need in order to complete the study. You will need a minimum of 3 people, the following tools and materials: a GPS unit, a pressure gauge and clear rubber hose, a 25 to 30 liter bucket, a float, which can be assembled from a ping pong bowl and a bolt nut, measuring tape, a conductivity meter, salt, pre-measured into 100 gram portions, a large 1.5 liter bottle, and a stopwatch. Finally, it is also important to remember that when assessing the potential of a microhydro system, seasonal variations in flow need to be considered. It is best to conduct a feasibility study during dry season or low flow periods throughout the year, to ensure that we calculate the minimum potential of the microhydro system and do not design a system that is too large. Before setting out from your community, make sure your GPS is turned on, calibrated, and set to tracking. Mark a waypoint at the general location of the community. Also, note the elevation at your starting point, which should appear on your GPS. The first location you will try to determine is your intake site. As you travel to the potential intake location, take note of the terrain and other key geographical features, and potential sites and routes for the powerhouse, penstock, and forebay. When selecting sites for the key features of microhydro systems, we must be sure to consider a number of factors that will determine the successful functionality and maintenance of the microhydro system, and ensure proper considerations of all parts of the final microhydro system. When selecting an appropriate intake site, look for important natural features for consideration of intake construction. Boulders can be obstructions, but they can also form natural features to channel water through a smaller space and the building blocks of intake construction. Rock walls may also be used to aid in intake construction, forming one or both sides of the eventual water catchment area. Narrower portions of streams would be ideal because they provide an easier space for measuring flow and can typically be natural features to help in intake construction as well. Small waterfalls can also be considered as suitable sites to measure flow, and waterfalls are also normally located below natural water catchment areas that can be used to construct an intake. When considering a good site for the forebay, it is important to find a portion of flat ground not too far from the intake. The powerhouse will also require flat ground near enough to the stream source to allow room for the tail race to discharge water back to the stream. Now we move on to measure head, one of the key variables in sizing a microhydro system. Head will be important in determining the size in almost all of the key features. In hydrological terms, head is a measurement of pressure, which can be discerned by measuring the vertical distance between the top of the source of the water, that's in the intake or the forebay, to the anticipated point of generation at the powerhouse. For the purposes of the feasibility study, this measurement does not need to be 100% precise, but there are several methods available to determine an appropriate reading. There are 3 instruments that we use to help us measure head. First, a GPS. To use the GPS to measure head, simply record the elevation reading from the GPS once you are at the intake site and at the forebay site if you have determined it. Upon arriving at this site, rest the GPS on a flat surface for a few moments to allow it to calibrate before recording the reading. Note that while this is the easiest and fastest method of determining head, it is also the least reliable and should be paired with one or both of the other methods described. The pressure gauge is able to provide you with a pressure reading as a liquid or gas exerts pressure on its internal mechanisms. This reading is expressed on your pressure gauge in bar and psi. For the purposes of the feasibility study, pay attention only to the bar reading. Attach the pressure gauge to the hose in the following manner. You will have to take multiple readings in order to calculate the total head, so assign one member of your team to note the readings, one member to fill the hose, and one to hold the pressure gauge and announce the reading. The filler should stand upriver, fill the hose, with the reader and note taker recording the reading. Ensure there are no air bubbles in the hose. Once a reading has been noted, the reader should wait for the filler to arrive at his location before proceeding to the next point of measurement. Repeat this process until arriving at your prospective powerhouse site. The other key variable that factors into sizing a microhydro system is flow. Flow is the measure of a unit of water over a unit of time, which for our purposes is expressed in liters per second, and in the units Q in the power equation. The volume of water that is able to pass through the turbine in conjunction with the pressure generated by the vertical drop that is available together determine the potential size of a microhydro system. When determining a site to measure flow, we must be conscious of the profile and characteristics of the river or stream we are measuring. For instance, as we travel upstream, we must take note of portions where the stream diverges. If we decide to position an intake above a diversion, we have to remember that we will not have access to the same flow of water that we would have access to downstream. Now, there are 3 methods of measuring flow that we will discuss here today. First, the bucket method. The most simple method for measuring flow requires the use of only a bucket and a stopwatch. You'll need one person to hold the bucket, one to monitor the stopwatch, and someone to take notes. Note that the bucket is not an effective method for measuring large rivers. First, try and identify a portion of the stream where the water is channeled into a small waterfall. If no waterfall exists, you can often create one by repositioning small stones in the riverbed. The person holding the bucket will be positioned under the waterfall, filling the bucket while the person monitoring the stopwatch counts down the time it takes to fill the bucket. Repeat this process several times to get a range of results, then take the average of those results. For example, let's assume we have a 30-liter bucket and it takes 3 seconds to fill the bucket. This means we can assume the flow to be 10 liters per second. Second, the float method. The float method is slightly more complicated but does not require any advanced tools or equipment and can be used in larger and flatter rivers. This method relies on 2 variables. First, the time it will take for a flotation device to travel across a section of the stream. Second, the volume of the section of stream that the float is traveling across. To take these measurements, you will need a measuring tape, a float, and a stopwatch. You will need to assign a note taker and a timekeeper. Identify a suitable site to conduct the measurement. Ideally, this will be a portion of the river that is relatively flat. You do not want to have rapids or eddies interfering with the movement of the float. Now to the measurements. First, we need to find the volume. We do this by measuring off a small section of the river or stream. For a smaller stream, 5 to 10 meters should be sufficient. You then take note of the cross-sectional area of the river. Start by measuring the length and width of the river, drawing an imaginary cross-section area in your notepad. Using the tape measure, measure out equidistant points along the width and length of the river. Then, at those same points, measure the depth of the river. When you take note of these results, you end up with a cross-section of the portion of river you are measuring. Calculate the average of the depth measurements along the cross-section, then multiply that by the width to calculate the area. With the area determined, drop the float in the upstream portion of the river cross-section. The timekeeper takes note of the time it will take for the float to travel to the end of your cross-section. Again, take this measurement several times to obtain an average. You can then calculate the velocity, which measures the displacement or change in position over the change in time, represented by this equation. Speed, or rate, is a scalar quantity that measures the distance traveled over the change in time, represented by this equation. To calculate the flow, or discharge, multiply the area by the velocity. Finally, the conductivity meter. Measuring flow using a conductivity meter enables an accurate flow reading by determining how quickly a premixed solution passes through your meter. Conductivity meters consist of electrodes and sensors that detect changes in conductivity, among other variables, like temperature. For this exercise, we are concerned only with the conductivity reading, expressed in microsiemens. Conductivity changes occur when liquid flow causes movement of the boundary between two solutions of differing conductivity. By adding a salt-diluted solution to the stream, we temporarily change the conductivity level of that stream. As we measure the rate and level to which the conductivity changes, we are able to plot the results along a bell curve that can be used to determine the flow. For this section, you will need your conductivity meter, stopwatch, and salt packets. Assign a member of the team to be your note-taker and reader, one member to be your timekeeper, and one to travel upstream to place the solution into the river. Pre-mix the salt solution by mixing the salt and river water from your location in a container. Ensure the salt is dissolved before pouring it back into the river. The note-taker and reader should position themselves between 30 and 100 meters downstream of the pourer. They should also locate themselves in a narrower part of the river with the conductivity meter electrodes placed inside. Again, try to avoid places with eddies and rapids, and take note of stream diversions. Record the base microsiemens reading, which should be relatively stable, before placing the solution into the water. Once the solution begins passing through the electrodes, you will notice the microsiemens value start to increase. Take note and record the readings at 5-second intervals. Continue until the reading comes back to the base microsiemens value.